Now today I will discuss about the internal field. Okay, for explaining the internal field of a solid material. So if you will take any solid material, so internal field. If you want to explain the internal field, what is the internal field means? So let us take any atom inside the material. Any atom inside the material. What are the total electric field act on that material? Total field act on that material, that is called as internal field or local field or Lorentz field. So let us take point A, that means atom A, any atom A. Okay, so and that atom, so if you apply the external electric field, how much electric field act on that atom, we are calculating now. Okay, for that what we are doing means, so let us take here one part. Let us take any material, any dielectric material here. So in that dielectric material, just I am applying the electric field. So that means for that I am taking one capacitor, that means two metal plates. For that two metal plates, so one metal plate is connected to the positive terminal of the battery, another metal plate is connected to the negative terminal of the battery, positive terminal of the battery and negative terminal of the battery. So if one terminal is connected to the positive, that means one metal plate is connected to the positive terminal. That means what happened here? Positive charge is developed on this metal plate. Positive charge is developed on this metal plate. This metal plate is connected to the negative terminal. That's why what happened? Negative charges. What is that? Induced on that here, developed on that this metal plate. Negative charge is developed in this metal plate. Now I am placing one dielectric material in between the two metal plates. Okay, if you place the dielectric material inside the dielectric means what happened? Inside the electric field. So if you place the dielectric material inside the capacitor means what happened? So these dielectric material is polarized. These dielectric materials are polarized. So we are applying here positive field. That means what is the electric field direction? Positive to negative. Here applied field direction is so like this direction. Applied field direction is like this direction. Because of these electric field, what happened here? So induced charge will be developed in this surface as well as, so induced charge will be developed in this surface. That separation of charge here, that means charge is induced on the dielectric material, that is called as polarization here. So that means, so here here negative charge is induced on the surface of this side, and here positive charge is induced on the surface of the dielectric material, Okay, so now, so because of the applied electric field, what happened? So some charge is induced on the dielectric material. So negative charge is induced on the positive plate and positive charge induced in the side of negative plate. Now, so what is the direction of electric field? This electric field, induced electric field. So this is the induced, that means because here charge particles, negative charge particles are induced this side, positive charge particles are induced this side. So because of the charge separation here, what happened? Here also some electric field will be developed. So what is the field direction? That field direction is positive to negative. That means that is opposite direction to the applied, whatever the previously applied field. So that is, let us take here. So this is E2. Okay, let us take this is E1. Okay, now, so that means how much electric field acting on this particle here? So suppose we are taking at the center of the material and taking one atom. Okay, so in that atom, how much electric field acting? So because of the applied electric field, so applied external field will be there now. So because of that what happened? Even electric field will be acting. So now similarly so because of the induced charge, so there is some electric field acting. So because of the applied field, what happened here? E1 electric field. And so because of these induced charges, so there is some E2 electric field will be act on that atom. Now consider, so inside the atom, so many materials another atoms will be present. So due to those atoms, how much electric field act on that? So first I am considering, so one is the applied electric field. So because of that means due to the capacitor plates. So E1 electric field act on the atom A. So next, so E2 means due to induced charge, some electric field act on the atom A. So that is E2. Okay. Now, so inside the material, so many atoms will be present. Due to those atoms also, some electric field will be occur. That means act on that atom. So that electric field we have to calculate here. For that, I am taking. Okay, one symmetric shape, one symmetric sphere, like sphere shape, symmetric sphere I am considering here. In that, so I am considering one symmetric sphere. Either it will be like a cavity. So in that symmetric cavity, there is so many number of atoms will be present. Each atom will act as one dipole. That means so many number of dipoles will be there. Okay, so because of those dipoles, what happened here? Some charge is induced. Suppose here negative charge is induced. In this side, negative charge is induced. Similarly, in this side, positive charge is induced. Okay, so that means it depends on the here surface. It will be charge induced. Okay, so now, so one side negative charge is induced, another side positive charge is induced here. Okay, and so inside the atom also so many number of dipoles will be there. Okay, so now here, so there is some charge due to those dipoles. So that means each dipole having dipole momentum. Because of those dipoles, some electric field will be act on a point A. That is E3. Similarly, so that means on the surface of the sphere, what happened? Charge is induced. Surface of the cavity, charge is induced. So due to those surface charge density, another electric field act on that point A. That is E4. Okay, so these are the total electric fields acting on the atom A, at point A. Okay, so that means total electric field EI is equal to EI. That means that is the induced electric internal field or local field or Lorentz field. That means EI is equal to, so E1 plus E2 plus E3 plus E4. This is the total charge acting on a atom A. Now we will calculate the individually. So what is the electric field due to capacitor? That is E1. Okay, what is the value? Of that means, suppose if you will take one capacitor, so that means capacitor means two parallel plates here. Separated at a certain distance. Capacitor is nothing but two parallel plates. So those parallel plates are separated at a certain distance. If you will take middle of the capacitor, what is the electric field acting on that? Means that is equal to, so here, that means what is the charge of the capacitor? Q by A. So epsilon naught. Epsilon naught is the permittivity. Epsilon naught is the permittivity of the medium here. So that means, so E1 means, so that means if you will take capacitor, so capacitor is nothing but two parallel plates. Due to these parallel plates, at the middle of the capacitor, some electric field will be acting on. That electric field E1 is equal to Q by epsilon naught. Q by epsilon naught. That means Q here, not Q. So sigma by epsilon naught. Sigma means surface charge density. Not here there is not a single charge. So there are so many charge particles will be there. So many charge particles will be there. That's why we are taking instead of Q. So we are taking sigma, surface charge density. Surface charge density of the plate. Okay. So that is called sigma. Sigma by epsilon naught. Okay. Now this is sigma by epsilon naught. Now we are placing here. Now we are placing dielectric material. Dielectric material. So now we are placing dielectric material means so total surface charge density will be changes. Okay. So that means so it will be equal to the displacement. Surface charge density is equal to the displacement d by epsilon naught. Okay. Now if you place the here dielectric material, what happened? Surface charge density will be changed. So that is equal to the displacement. So displacement d by epsilon naught. Okay. So now there is a relation between displacement and electric field and polarization. So that's why. So that relation is equal. D is equal to epsilon naught E plus P. Epsilon naught E plus P by epsilon naught. Epsilon naught. Okay. So this is the electric field E1. Electric field E1. Electric field due to the electric field due to E1, okay, due to the capacitor. If you simplify it, so we can get so E by epsilon naught plus P. Sorry, E plus P by epsilon naught. E plus P by epsilon naught. If you simplify it, we can get E plus P by epsilon naught. So that is the E1 value. That means this is electric field due to the capacitor. Electric field due to the capacitor. That means what is the electric field acting on a point T. Now, so E2. E2 means, so what is that? So due to these induced charges, what happened? Some electric field occur on a point A. So that is E2. So what is the formula here? Means surface charge density sigma S. Surface charge density sigma S by epsilon naught. Okay, surface charge density of the sigma S means here surface charge density of the dielectric material. Okay, that is sigma S. So sigma S by epsilon naught. That sigma S is, that means so we know that according to the definition of polarization, so polarization is numerically equal to the surface charge density. So polarization is numerically equal to the surface charge density. So that's why here we can write P by epsilon naught. P by epsilon naught. That is so due to capacitor surface charge density. Sorry, due to what is that? Dielectric surface charge density. Some electric field act on that. So that equal to E2 is equal to P by epsilon naught. Now similarly E3. So E3 means here electric. That means if you will take inside the material, we are assuming here one symmetrical sphere or symmetrical cavity. In that symmetrical cavity, there are so many number of dipoles. That means so many number of atoms will be there. Each atom will act as a dipole. Each atom will act as a one dipole. So that's why. So due to those dipoles, here so many dipoles will be present. Due to those dipoles, what happened? Electric field. How much electric field acting? So here, this is the we are considering here symmetric structure. So that's why. So what happened? So in case of symmetric shape of the material, so resultant dipole momentum will be 0. So there is no dipole momentum. Means total charge will be acting on that is 0. Okay, now coming to the electric field E4. So electric field E4 is nothing but here. So due to the surface charge. Due to the surface charge density of the spherical sphere. Here. Okay, that is the E4. Okay, so now for finding the surface charge density of the spherical sphere, okay, what we are doing means I am taking here. See here. So let us take the sphere I am taking here. This is the symmetric in shape. So for that I am considering small charge dq, small charge dq, and its area will be ds. Area will be ds. Okay. Now due to that small charge, so some electric field acting on that point A. So due to that small charge, some electric field acting on that point A. Okay. So that means according to the sphere, so what is the charge acting on that sphere means? So E4 is equal to 1 by 4 pi epsilon naught, 1 by 4 pi epsilon naught into due to the small charge dq. Due to the, so here we are taking small charge, so that's why here we will take DE4. We are not taking total charges, only we are taking due to the small charge. So that's why, so there is a some electric field DE4 that equal 1 by 4 pi epsilon naught into Q by R square. Q by R square. R is the distance. Okay. So distance between the radius. That means here center I am taking a. So that's why. So this is the radius. So this also radius. Okay. Now here this is the spherical shape. Spherical shape means like a football shape. Okay. I am taking some small surface area on that. Small surface area means it will be, if you will take total around means, so it will be like a ring. It will be like a ring. Okay, so what is this? If you will take center of the ring, this is the center of the ring. I am joining that is the center of the ring. Let us take this is S. Let us take this is S. Okay, now I am joining the, so this from here to here. Okay, this is, let us take this is the P and this is the Q. This is the Q. Okay, so otherwise P is already there for us. That's why let us take R. Okay, let us take R. Okay, now so from this, so this small surface area, the small surface area making an angle with parallel axis theta, making an angle with parallel axis theta. Okay, and that small part making an angle d theta. Okay, so that means this is a sector. QR is the sector here. What is the sector means? So here QR is the sector. QR is the sector means what is the sector? So sector is equal to, we can write R into d theta, R into d theta. And so now radius of the ring. So radius of the ring means, so this is the radius of the ring. Okay, so from this triangle A, from this triangle ASR, from this triangle ASR, so this angle is 90 degrees here, this angle is 90 degrees here from this triangle. So that means RS is equal to, so that means here sin theta is equal to, we can write sin theta is equal to, we can write RS by AR. Yeah. Okay, AR means radius of the sphere. See here, AR is the radius of the sphere here. Okay, so that's why. So RS is equal to, we can write into, so small r sin theta. Small r sin theta. This is the radius of the ring. Radius of the ring. So this is the, that means width of the ring. Width of the ring. So now for finding the, here we are taking small charge dq now. So that means for finding the polarization here. That means yeah. So dq value we have to calculate. Dq value we have to calculate means, so here, so that means some polarization will occur. So that polarization is P. So let us take that polarization direction will be, so like this direction. Okay. So that polarization also divided into, so two parts. One is the horizontal component. Suppose if you will take these two parts. So here also some polarization will occur. Here also some polarization will occur. So this is, we can convert it into two parts. So one is the horizontal direction, one is the vertical direction. So vertical direction is peak sin theta. So vertical directions are opposite in direction. So that's why these two are cancelled out with each other. These two are cancelled out with each other. Only resulting is P cos theta. P cos theta. Okay. Now P cos theta is equal to, so dq by dA. dq by dA. From this we can calculate the dq value. Now dq is equal to P cos theta into dA. P cos theta into dA. Okay. Now, so we know that here, what is that area? So area of the ring we have to calculate here. So dA means area of the ring. Area of the ring means, okay, area of the ring we have to calculate here. Area of the ring. So area of the ring means, so circumference of the ring into width. Circumference of the ring. Circumference means 2 pi r. Circumference means 2 pi into radius of the ring. What is the radius here? So this is RS is the radius. That means we can write R sin theta. R sin theta. into, so width of the ring. So this is the width of the ring. Q is equal to R into d theta. R into d theta. So now this is the area. So from this area we can calculate dq. So dq is equal to P cos theta into so this area dA. So 2 pi into sin theta r d theta. So finally dq is equal to, so 2 pi r p into cos theta sin theta. So this is the charge dq. Now coming to the, so electric field dE4 is equal to, if you substitute this value here, 1 by 4 pi epsilon naught into 2 pi, here it will come. So here r sin theta will be there, here r d theta will be there. So 2 pi r square it will be, 2 pi r square. So 2 pi r square into p cos theta. So that means here, so so cos theta and sin theta d theta, by r square gets cancelled. So finally, by using this equation, see here, so dE4 is equal to what we can calculate means 1 by, so 2 pi gets cancelled, so 1 by 2 will be remaining, 2 epsilon naught is remaining, and so P cos theta and sin theta d theta will be there. So now this is dE4. So this dE4 is the, so charge acting on a point A. So this also divided into two components. One is the horizontal component, another one is the vertical component. Similarly, vertical components are the cancel out with each other. So horizontal component, so remaining is the horizontal component dE4 cos theta. So if you want total field, electric field means, so if you want to integrate it, 0 to pi into dE4 cos theta. Okay, now E4 is equal to, so if you substitute that value means we can get, if you solve this total equation after substituting this equation, if you solve this equation means we can get, so E plus, so P by 3 epsilon naught. If you solve this, so after substituting the dE4 value here, so we can calculate it means E value we can get, so E plus P by 3 epsilon naught. So if you will take total electric field, EA is equal to, so we know that, so here E plus P by epsilon naught. Okay, so E plus P by epsilon naught. So only we will get only P by 3 epsilon naught, I think. So here we can get only, so P by 3 epsilon naught. If you solve it, so P by 3 epsilon naught. So plus, so here direction, see the direction will be minus. That's why we have to take minus here. So minus P by epsilon naught. So plus third value, E3 value is 0 and E4 value is P by 3 epsilon naught. So epsilon naught gets cancelled. So resultant field EA is equal to, so E plus P by 3 epsilon naught. Okay, so this is the local field. So local field acting on a inside the atom A. So this is about the local field. By using this local field, so we can calculate the Clausius-Mossetti equation. So the Clausius-Mossetti equation relate the, so macroparticles, relation between the macroparticle into microparticles. Okay, so tomorrow we will discuss about the Clausius-Mossetti equation. Thank you very much.